Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and good morning to all of you. All right, so next we go for the chapter 4 is the oscilloscope. Okay, for this chapter 4 is mostly a lot of theory, a lot of theory. So you can see on the slide. Okay, so the new outcome for chapter 4 is to able to operate oscilloscope to display and analyze the waveform of electrical signal lah. Alright, so the function of the oscilloscope is the one instrument that we can measure or we can do the measurement or do analysis on the electrical signal lah. Okay, so the objective of these topics is first is the list of major subsystem of an oscilloscopes. Okay, so this topic will be covered for the analogs. Okay, analog oscilloscope lah. So nowadays I think on the FKE, okay, and FKE lab, so totally our oscilloscope using the digital one. So this, but we have to know the analogs lah, analogs. Okay, so before this we use the analog oscilloscope. Nowadays I think most of the lab we use the digital oscilloscope lah, but there will be same concept lah. Okay, and then second objective will be do the basic operation and calibrate an oscilloscope. Okay, so before we do some measurement, we can do analysis on the electrical signal. So we have to do a calibration. Okay, so on the oscilloscope, very simple lah. For digital oscilloscope, very simple, straightforward calibrate oscilloscope before we do some measurements. All right. And then objective number 3 will be determine the frequency and amplitude of the signals displayed on the screen lah. So before this, for the analog, we use the CRT screen. Now we use the digital screen. And then we have to compute phase angles. Okay, on the oscilloscope, you have to know how to measure the waveform on the electrical signal lah. So that is on the calculation part lah, because we have to know the scale that you use to measure the every waveform that we use lah. We use to measure. Okay, all right. So this is some introduction for the oscilloscopes. Okay, so we know as the cathode ray oscilloscopes. Okay, so the cathode ray oscilloscope (CRO) generally refers to as the oscilloscope that probably the most versatile electrical measuring instrument lah. Okay, because we use the oscilloscope, we can use the current, we can use the voltage and so on. Okay, the electrical parameter can be observed with the oscilloscope AC or DC voltage. Okay, indirect measurement of the AC or DC current, time, frequency, phase angles, and the wide range of the waveform evolution such as rise time, fall time, ringing, and overshoot. Okay, using the oscilloscope, we can use for DC or AC voltage. Okay, so also we can measure the frequency. Okay, frequency, and then also the time, and also we can calculate the rise time, okay, falling time, and also we can calculate the overshoot. That's why most of the okay, that's why we call the most versatile for electrical measurement instrument for this oscilloscope. Okay, oscilloscope. All right, so the physical quantities such as pressure, strain, temperature, and acceleration can be measured by using the transducer to convert in physical parameter to an equivalent voltage lah. Okay, so for example, like pressure. So normally pressure in analogs. Okay, so and then we have to use the some physical parameter to convert. Normally on our pressure, our sensor output will be on the voltage lah. So from this voltage, we have to convert into pressure. So this one involves the mathematical lah. So based on depends on the sensor that you use. Okay, they have the mathematical modeling for that sensor. So from output voltage, so you have to convert into the pressure that you set lah. Okay, so the oscilloscope consists of the following major subsystem. So they have the cathode ray tube (CRT), right? So vertical amplifier, horizontal amplifier, sweep generator, trigger circuit, and associated power supply lah. So this is a component component for the oscilloscopes. Okay, next, the oscilloscope is basically an electron beam voltmeter. Okay, so the heart of oscilloscope is the CRT, which make the applied signal visible by deflection of thin beam of the electron. Right, so practically the electron has no weight, okay, and no inertia. Therefore, the beam of electron can be moved to follow varying, okay, at the rate of million of time or per second, right? Thus, the electron beam follow rapid variation in the signal voltage and trace a visible part on the CRT screen. Okay, so in this way, rapid variation, pulsation or transient are reproduced, and the operator can observe the waveform as well as measure amplitude at any instant of time. Okay, so this can be used in the any fields where the parameter can be converted into a proportional voltage for observation. Okay, for example, like meteorology, okay, biology and medicine. Okay, so this is a figure, okay, figure for basic, okay, cathode ray tube construction. Okay, actually this is basic construction of oscilloscope lah. So you can see this is electric guns. Okay, so on the electric gun we have the filaments and cathode, and also we have the glass envelope here. Okay, this one is the glass envelopes, and so this part, the first part is the triode section, and also we have to focusing lah, okay, on this part. And then after the section part, next part is the deflection lah. So on the deflection we have the vertical deflection plate, and also we have the horizontal lah. Okay, so this one is the verticals, okay, difficult deflection plate, and this one is horizontal deflection plate lah. Okay, and then this is a post deflection oscillation lah. So this is we call the resistive helix. Okay, all right, so this is a basic cathode ray tube construction. Okay, so the basic operation of oscilloscopes, the CRO depends on the movement on the electron beams, which is bombarded on the screen coated with the fluorescent material to produce the visible spot lah. Okay, if the electron beam is deflected on the vertical, okay, vertical is the x-axis and horizontal for the y-axis, okay, the two-dimensional display is produced. Okay, so the beam is deflected at the constant rate relative of time along the x-axis and deflected along the y-axis in response to the signal, such as a voltage lah. So this produces a time-dependent variation of the input voltage. Okay, so the beam of electron is generated by the cathode and directed to the screen, causing the proper coating on the screen to glow where is the electron strike. Okay, so the electron beam is deflected vertically and horizontally by externally applied voltage. Okay, so on the triode section, so you can see on the triode section, that's why we consist of the okay, on the triode section, on the basic figure you can see we consist of cathode, grid and anode. Okay, so the grid is the nickel cup with the hole in it, okay, almost completely enclose the cathode. Okay, so the cathode, there is some produced by nickels. Okay, is the cylindrical shape with the flats, okay, oxide coated, okay, electron emitting surface directed towards the hole in the grids. Okay, cathode heating is provided by an inside filament. Okay, so the cathode is typically held at approximately negative 2 volts, okay, 2 kilovolts, and the grid potential is adjustable from the approximately 2000 volt to negative 2000 volt to negative to 2050 volts. So the grid cathode potential control the electron flow from the cathode and thus control the number of electron directed to the screen. So in other words, okay, So the grid potential control is the brightness controller. So the large number of electrons striking one point will be cause the screen to glow brightly. Otherwise, the small number will be produce the dim glow. Okay. So next, the first anode A1 open at one and close at the other ends. So with the hole at the center of the closed end. Okay, since A1 is the grounded and the cathode is at a higher negative potential. So A1 is the highly positive with respect to the cathodes. Okay, so this causes electron to be accelerated from the cathode through the holes in the grid and anode to the focusing section. Okay, so in other words, A1 okay provide the accelerating fields to draw the electron from the cathodes, and the hole in A1 limit the initial cross section of the electron beams. Okay, this is on this part on the triode section. Okay, next we go for the section focusing section. Focusing section electrodes A1, A2, and A3 are referred to as an electron lens. Okay, so the function of electron lens is to focus the electron to a fine point on the screen. So A3 and A1 are held at ground potential, while A2 is adjustable around 2 kilovolt. Okay, 2 kilovolts. So the result of the potential difference between anodes is the called equipotential lines. So the line 1 might be 100, okay, negative 100 volts, while the line 2 might be negative 500 volts. On the crossing the equipotent lines, so the electron experience a force that change the direction of the travel towards right angles with respect to the equipotential lines. Okay, so the shape of the line within the A1 produce the convergence force on the electron beam, and those within A3 produce the divergent force. Okay, so this is, you can see the potential difference between the A1s. Okay, this is for A1, A2, and A3. Okay, so this potential difference between the electron A1, A2, A3 set up equipotential line that exert convergence and divergence force on the electron beam. Okay, so on this part focusing, okay, on the focusing section. Okay, so on next section is the deflection. Okay, the deflection section, if the horizontal and vertical plate were grounded or left unconnected, okay, so the beam of electron would pass between each pair of the plate and strike the center of oscilloscope screen. Right, so they would produce a bright glowing points. Okay, when one plate of the pair of the deflection plate has the positive voltage, and another one has the negative potential, so the electron in the beam are attracted toward the positive plate and repelled from the negative plates. Okay, so next, this plate arranged in two pair. Okay, H1 and H2 for the deflection of the beam horizontally, and V1 and V2 for the deflection it vertically lah. Okay, as shown in the figure 4.2. Okay, so when the plate are at the zero voltage, the beam is midway between them, and the spot is in the center of the screen. Okay, so when H1 is the positive with respect to the cathode, okay, that means all other plate are at zero voltage. It attract the beam and the spot move horizontally to the left. All right, so when H2 is positive, it attract the beam and spot move horizontally to the right. All right, so when V1 is the positive and spot move vertically upwards, and when the V2 positive, so the spot move downwards. Okay, so next topic will be measurement of the voltage, frequency, and phase angle. So the range application of an oscilloscope vary from the basic voltage measurement and the waveform observation to highly specialist application in all area of science, engineering, and technology. All right. So for the voltage measurement, the most direct voltage measurement are made with oscilloscope is the peak to peak value. Okay. So the RMS value can then easily calculate from the peak to peak value lah. All right. Okay, to measure the voltage from CRT display, so one must be observe the setting. Okay, this one we have to make sure. So the setting on the vertical attenuator expressed in the voltage per division and the peak of the peak deflection of the beam. All right, so that's why you can see on the vertical attenuation. Okay, and then we have to check on the peak to peak deflection of the beam lah. For example, the number of division. Okay, so the peak to peak value of the voltage is then computed as the, okay, this is a formula for calculate the voltage peak to peak lah. Okay, volt per division and then multiply per number of division per one. Okay, so this is formula to calculate the voltage peak to peak. Okay, all right, for frequency and phase measurement, right? So the period and frequency of the periodic signal are easily measured with an oscilloscopes. Okay, the waveform must be displayed such that the complete cycle is displayed on the CRT screens. Okay, the accuracy is generally improved if the single cycle display fill as much the horizontal distance across the screen as possible. Okay, and then the period is calculated as the, okay, so this is, you can check on the time divisions. Okay, okay, time per division and multiply number of division per cycle lah. Okay, that is formula to calculate the period. Okay, and then frequency determination is using the formula lah. F equals to 1 over T. All right, so this is for phase difference. Okay, the phase difference. Okay, so this is to calculate the phase difference is the phase difference in division multiplied by degrees per division. All right, this is some example lah. Example. All right, so you can see the input signal of A. Okay, so this is a signal for A. Okay, actually this one is a peak to peak from this one to this one. Okay, for the signal B, and for signal A from this one to this one lah. Okay. All right, so this is, we call the voltage peak to peak lah. Okay, for signal A and signal B. Okay, so for example, okay, volt per division we set as the 100 millivolt. Okay, 100 millivolt. That means this okay, this square is the 100 millivolt. Okay, 100 millivolts per division. That means one division is the 100 millivolts lah. And then the time, this is for the time lah. The time is one division is, this we call one division. Okay, it's a 0.5 millisecond per division. That means this is 0.5, 0.5, 0.5 millis per second lah. That's the concept of the oscilloscope. Okay, this one division is the 100 millivolt. Okay, this is, for example, 100 millivolt, 100 millivolt, and 100 millivolts. Okay, this is how we measure the oscilloscope lah. Okay, so next for Lisa-Joyce figure. So if we allow one AC signal to deflect the beam up and down, connect that AC voltage source to the vertical deflection plates, and another AC signal to deflect the beam left and right. So using the other pair of deflection plates, so patterns will be produced on the screen of CRT indicates of the ratio of these two AC frequencies. This pattern we call as a Lisa-Joyce figure lah, and are common means of the comparative frequency measurement in electronics. Okay. All right. So this is some example. All right. So Lisa-Joyce figure formed by two AC voltage in phase. This means in the same frequency, which each other. All right. It will be same frequency. Okay, you can see this one. If the two AC voltage are not in the phase which each other, okay, for example, okay, the phase shift is exactly 90 degrees between the two signal, and if the amplitude are equal, so this is our output lah. Okay, this is we call the Lisa-Joyce figure. Okay, that means we have the same frequency. Okay, but the phase shift exactly the 90 degrees between two signal, and amplitude are equals. Okay, so this is the Lisa-Joyce figure. Okay. Okay, if we have two AC signal directly opposing one another is in phase, okay, 180 shift, so we will end up with the line again. So only this time it will be oriented in the opposite direction. Okay, so this is Lisa figure. Okay, the same frequency, but the okay, they're opposing one another in phase 180 shift lah. Okay, 180 shift, so will be like this one. The line will be like this. Okay, so when we are faced with the signal frequency that are not in the same, so Lisa-Joyce figure get quite a bit more complex. Okay, consider the following example, and they are given vertical and horizontal ratio. All right, so this is a you can see on the Lisa figure. So horizontal frequency is twice of the vertical. Okay. And then the more complex of the ratio between the horizontal and vertical frequency, the more complex of Lisa-Joyce figure lah. So you can see we have another one shape. Okay, another shape lah. So the following figure illustration of three ratio one frequency ratio between the horizontal and vertical lah. All right, one and three. Okay, 3 and 1 3 and 1 frequency ratio. Okay, between the horizontal and the vertical lah. So we can get this Lisa-Joyce figure, right? So for example, if we have three with two frequency ratio, okay, that means horizontal is 3 and vertical is 2, so we can get this one. So this is we call the Lisa-Joyce figure lah. For example, like okay, the horizontal is the 3 and vertical is 2. Okay, so for mathematical equation, okay, so the number of horizontal tangency divided by number of vertical tangency, right? So this is formula lah, mathematical expression for this one. Okay, so overview of the digital storage of oscilloscopes. So the digital storage oscilloscope of DSO for short, okay, is now the preferred type of the most industrial application. Although simple analog CRO are still used by the hobbyists, okay, it replaced the unreliable storage method used in the analog storage scope with the digital memory lah. So that's why nowadays, if you use the digital, oscilloscope, actually we can save directly, okay, using the USB, USB or any storage lah. So automatically our signal we can store lah. Okay, we can store the data as long as required without degradation. Okay, degradation. It also allows complex processing of the signal with high-speed digital signal processing circuits. So the vertical input instead of driving the vertical amplifier, so the digitized by an analog to digital converter to create the data set that is stored in the memory of the microprocessor. So the data set is processed and then sent to the display. So which is early DSO was a cathode ray tube, but it's now more likely to be a LCD flat panel. So the DSO with the color LCD display are commons. Okay, you can see this one. So this is analog and this one is the digital. All right, digital oscilloscope. All right, so the data can be sent over the lens or one for the processing or achieving. So the scope on signal analysis software can extract many useful time domain features lah. For example, like we can calculate the rise time, pulse, switch, amplitude, okay. Also the overshoots, falling time, and so on lah. Frequency spectra, histogram, statistical persistent mass, and the large number of parameters meaningful to engineers in specialized fields such as telecommunication, disk drive analysis, and power electronics. Okay. All right. So that's all for theory for the oscilloscope. Okay, for the calculation normally on the how to measure. Okay, for example, you can see this waveform on the oscilloscope. Okay, for example, this waveform, how to analyze this waveform. Okay, that is on the oscilloscope. So for example, from this waveform, we have to know the time division of voltage per division. Then we can every division we have to calculate with this one, multiply with times or vote per division. Okay, that's all for theory for the oscilloscopes. All right, so that's all for chapter 4. Right, so next we go for the example of the oscilloscope. Okay, thank you very much.